Hello, everyone. We came to our final technical lecture where I'm going to spend about 30 to 40 minutes talking, giving you an introduction to artificial intelligence and a brief definition of Industry 4.0. First, what is artificial intelligence? What comes to your mind when you think about artificial intelligence? I think for most of us, we think about this, right? Terminator, the robot apocalypse. For the younger among us, maybe we think about Dolores from Westworld, also robot apocalypse. Um, or for someone like me, we're gonna go right back to the 20s, and we can move back to the Greeks. The Greeks had an idea about an artificial kind of robot protector. This back in 2000 years, back 2000 years ago. So it's somehow at our back of our there's a very primitive archetype of most a more intelligent being taking over our lives and destroying the society. But in more rational terms, artificial intelligence is just the design and application of computer algorithms of a particular kind. And it's nothing else. There's nothing intelligent in artificial intelligence. The intelligence comes from the humans designing the tools. The original, we can look back at the original definition of AI. This was defining the workshop, the seminar that gave birth to artificial intelligence in 1956, called the Dartmouth Summer Research on Artificial Intelligence. They had the founding fathers of artificial intelligence, such as Marvin Minsky from MIT, John McCarthy, who was the person who coined the term artificial intelligence, was from Stanford, Claude Shannon, creator of information theory, McCulloch, the person who defined mathematically the first neuron, McCulloch-Pitts. There's a great paper it was one of the best papers I've ever read. John Nash was the Nobel Prize in Economics in '94. Herbert Simon was also another Nobel Prize in Economics in '78. So they got together in Dartmouth for about 3 weeks. They had time for a 3-week break in those days to discuss this thing, right? So this is the main definition, the original definition of artificial intelligence. It's the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. Now, I think this is the key aspect, right? The key aspects. Oops, let me get a pen. Key aspect is to produce a computer program or a set of algorithms capable of solving the kinds of problems now reserved for humans. Now, what are the kinds of problems reserved for humans? It changes, right? If you go back to the 17th century or 18th century, the kinds of problems that machines were substituting humans were in the production of cloth, right? Well, the first industrial revolution was on the cloth industry, right? So production of clothes and other goods. Now, there are quite a few other definitions, but I prefer to define AI by its various subfields, such as automated problem solving. This is one of the most traditional areas of AI, which given a problem description can be a mathematics problem, can be a problem in biology, or those kinds of problems that I like to solve with AI, which are these little kind of puzzles involving distinct types of objects that we can sort of relate to the way we reason about the spatial world So we generate an algorithm pretty much similar to the, not similar, but using the same elements that you used on your Zoomo project to give us a solution to the problem. Not only to solve the problem, but to give us the steps for a proper solution to the puzzle. Knowledge representation and reasoning and planning. This relates to all sorts of knowledge. There are tutoring systems where we implement the knowledge. Say, if you want to teach a student biology, you represent the whole knowledge of a biology book in an algorithm that's going to then be used to teach a particular student. And these algorithms, they have some sort of model of the student, so they sort of can interpret the weak points of the students and try to enhance. And we can use knowledge representation in any sort of field. This is what is usually called expert systems, especially in medicine. In medicine, it's quite famous. You just input medical knowledge, you put the symptoms, and the algorithm is going to output the diagnosis and the potential medicine to be used for each case. Probabilistic reasoning is a type of knowledge representation where here we include the uncertainties, especially in uncertainties, all sorts of information, but most particularly in terms of robots, robot sensors that are intrinsically uncertain. So we have to use probabilistic reasoning for allowing the robot to make inferences about the world. Natural language processing, you get Alexa or Cortana or one of these assistants, Google Assistant. And there is another field of artificial intelligence is understanding and the use of natural language. That's called natural language processing. Multi-agent systems. So you probably get spam every day on your email address due to multi-agents spread it out in the internet, and they are quite well organized, and it's actually what we call a society of artificial intelligence. Intelligent robotics is similar to multi-agent systems, but now robots are actually physical systems, right? Machine learning, which we're going to see a little bit more in depth in this lecture, which is the task of having an algorithm that given a set of examples, it learns a particular pattern, and so on. There's quite a few systems and quite a few of algorithms in artificial intelligence are already in place. We already use it. So Google, the search engine, was born in Stanford Artificial Intelligence Lab. A search engine is intrinsically an artificial intelligence tool, algorithm. GPS navigation, whoever uses Google Maps is using GPS navigation, is using an artificial intelligence algorithm that finds the shortest path on a graph. Spam filtering that decides which messages are spam, so that it's put on your trash box automatically or spam box. E-commerce, there's loads of artificial intelligence in e-commerce, especially when you're dealing with these auctioning systems like eBay, auctioning sites like eBay and others. Right. So various subfields. These are all defined on this book. It has about 500 pages. There are 20 chapters, each chapter dealing with a distinct aspect of artificial intelligence. And I used to spend a whole year teaching the entire book in another university. Now, okay, so this in a very brief terms, that's all of the these are the most important fields or subfields of artificial intelligence. Now, so this is a nice diagram where you have artificial intelligence is the big kind of green circle that's defined by any system that leverages human capacities for learning, perception, and interaction, all at a level of complexity that ultimately supersedes our own abilities. Within this field of artificial intelligence, there is a subfield of machine learning. It's a subset of AI that involves programming systems to perform a specific task without having to code rule-based instructions. And what today is quite famous, and what we're going to spend 10 minutes talking about, is deep learning, which is also a subfield of machine learning. There is a subfield of artificial intelligence, right? Deep learning is a subset of machine learning algorithms where systems can learn hidden patterns from data by themselves, combine them together, and build much more efficient decision systems. So there are actually three kinds of machine learning systems. There are supervised learning, where you get the input are a bunch of data with labels. We're going to see one example of supervised learning in the labs this week, where it tries to classify your data, and given that as it's learning, it's going to make errors, and the errors are fed back into the learning system, and it kind of fits its parameters in what we call in a network. That's one of the techniques in neural networks. We've adjust the parameters of the neural network. Unsupervised learning, the data is without labels, so the unsupervised learning tries to learn classes of things. And whereas in supervised learning, the classes are given, and the system has to identify a new object, whether it belongs to one class or to another class, or to any number of classes. And reinforcement learning applies a kind of very rudimentary Pavlovian learning, where an artificial agent tries out actions in the environment and receives positive and negative rewards, and a deep learning system tries to optimize the rewards, tries to optimize to maximize future rewards. So in the end, the reinforcement learning agent will find the best actions around on its set of actions to be applied in each state to make the best of it, to maximize its rewards. This is a bit the scheme of supervised learning. What it does, it creates a kind of decision boundary where we can classify distinct types of data. Supervised learning, you just have the data, and it will try to find some sort of pattern, similarity between these items that are different from those other items. And reinforcement learning is this idea of applying actions, moving from one state to another state, and receiving a reward. And the idea is to find the best route that maximizes this reward. Now, let's take 10 minutes to learn at least one of these machine learning algorithms, which are the famous neural networks. And they are part of the deep learning system. So there are two types of networks: multi-layer, fully connected neural networks, and convolutional neural networks. The fundamental elements of both are the same. They are linear computing elements. They are called artificial neurons, and these are organized in terms of networks. These networks as vehicles for adaptively learning the parameters of decision functions via successive representations of training examples and patterns. In very general term, what a neuron, let's get a very primitive type of neuron that's called perceptron. Perceptron learns a linear boundary between linearly separable pattern classes. So if you have two classes, let's say C1 or C2, what a perceptron is building is trying to build the equation of this straight line. So it's using examples to build the equation of these straight lines. What do I mean by building the equation? By finding these two parameters, by finding the slope and the bias, by finding A and B, by a number of from a number of examples, so that it can find this decision boundary, such that any other element that once it's evaluated by this equation, if it's greater than 0, it will be classified as being part of the class C1. If it's less than 0, it will be classified as a class C2. You can imagine that this can be extended to multiple dimensions, to n dimensions, and obviously we can't use A, B, C, but then we're going to use indexes W1, which is the weight associated to the dimension x1, and this is the weight 2 associated to the dimension x2, and so on and so forth until to a dimension n that can be of any number. Now let's see the simplest case. This is the schematic diagram of a perceptron. Now this is exactly what I've written here. Oops, not this. Let me close this. So this is exactly what is written before. Now this is exactly what's written here, right? But on a more generalized term. This is written for n classes. So this is an equation of a straight line in multi-dimensions. Now, in this is basically what the perceptron does. It gets one example and applies this little linear equation to check whether the example has a value of closer to +1, and in this definition, or closer to -1. There is a decision boundary here, right? So if it's +1, this will be part of a class C1. If it's -1, this will be part of a class C2, for instance. That's how it is. That's how a perceptron works. Now, this is an example of how. Let me get it right. This is the perceptron in action. So for each example, it sort of tries to fit this straight line until the straight line doesn't move anymore. Then it finds exactly the boundary, the decision boundary, as separating these two groups. The groups of red dots and the group of, that's one class of objects, and the group of blue dots, there is another class of objects. Right? Let's see again. So this is done for every example that's given, every example that's input. It sort of uses the error. So in the first trial here, second trial, this is just basically putting. Let me get a pointer. These blue dots now are being classified as red dots because they are on this side of the straight line, right? So these are errors. These are errors. So the set of misclassified examples in the training data are then fed back into the neural network, or in this case a perceptron, to allow it to find a new straight line that's gonna then suffer the same procedure. It's gonna get the errors, and they're gonna fed back in a process called backpropagation in a neural network. It's gonna then fit a better line, a better decision boundary. And there's some maths behind it. We're not gonna get much into detail, but this is the simple perceptron that was defined back in 1960. This is not a neuron yet, and the only reason why this is not a neuron is that the decision boundary here is very hard. It's very hard. There cannot be an object that's more or less like +1, or the class that's defined by one of these values, right? So it's either is 1 or it is -1. There is no midterm here. Now, a perceptron, a neuron, on the other hand, is a kind of perceptron. This is a neuron. This is a neuron. It's a kind of perceptron with a smooth boundary. So I don't have a sharp decision boundary here, but I can have a portion. So if an object, when I calculate whether this one example falls within one side or at one side of a straight line of a decision boundary, or another decision side of the decision boundary, using this kind of equation, the linear equation. This is then fed. This is then part of this what we call activation function that's going to use a portion of it. So it's not going to be +1 or +2. It's going to be any number, right? Any number will be a kind of how close this each neuron is now measuring how close each example is to one of these classes. It's not defining the class yet, but it's telling you, it's giving you a number that's telling you how close that example is from each of these classes. And now this is one neuron, right? This is one neuron. What a neuron is just a linear approximator. It's just doing what we call, it's just doing regression, linear regression. But now imagine if we put these neurons, each neuron in a number of neurons in a network. So each entity here, each cell is one neuron of this kind here, each one approximating one particular linear, approximating one particular linear feature of whatever pattern is input to these neurons. And this becomes quite powerful, right? Quite powerful. We can play with it. Let me get this this web page on. Just give me a second. Okay, so this is then this is a neural network. So each one of these is a neuron. This is the kind of pattern that I want to find. You see that this is not a linear decision process, because I want to find a function that allows me to define each element that falls near these blue dots as blue, and each element that falls near these yellow dots as yellow, as another class, right? One is one class and the other is another class. And the decision boundary is not a line. It's not a straight line anymore. It is a circle. It is a circle. So this is a neural network that has as input two vectors, or two patterns here. And this has a hidden layer of neurons with 4 neurons, and it has 2 neurons output. It's a two-class process, right? One neuron is representing one class, say blue, and the other neuron, output neuron, is representing another class that is yellow. Let's see how this works by playing. Oh, it found the boundary. Right? It found easily the boundary with 4 neurons. Now, let's reduce the number of neurons. Let's stop this and reduce. Let's just put 2 neurons, 2 hidden neurons, and 2 input. It didn't find the boundary. It found something odd here. So basically, it's telling that all of these yellow dots, these neural networks, this neural network is defining them as well. Now it changed it a bit, right? So these yellow dots are now being classified as blue dots. So these are false positives. So these are errors from the neural network. That means that with this number of neurons, this neural network couldn't find the pattern defined. And you can play with this. Let's add a number of layers. Let's add a number of neurons for each layer. And press play. It found the pattern. And you can see what each neuron has found here, right? So this is the pattern. This is the linear pattern, the decision boundary represented by one neuron. This is the decision boundary represented by another neuron. This is by another. This is by another. And now these other neurons here are kind of combining the outputs of these neurons on the first layer by finding different layers. So you can see that now these decision boundaries are not linear anymore, but it is a linear combination of linear classifiers. And you can see that these neurons have quite complex decision boundaries here. And in the end, the final neurons, they do represent what are the objects, what are the classes that to be classified. All right. So this is what we call a multiply connected neural network. There are other types of neural networks. These are a lot more complex, but they are more modern, which are these, for instance. These are the convolutional neural networks. Convolutional neural networks yeah, just a more complex kind of neural networks. Our old neural networks, the one that you've just seen, they are still part of a convolutional neural net. That is the fully connected neural network that we've just seen in the example in that website. Now, a convolutional neural network works by using the entire input in finding filters, in finding features for the input. And in a kind of what, if you want to understand better, you should look into the definition of convolution. But what it is doing, in essence, is actually finding, it's running, so let's say this is an input image, it's running a filter here. It's more than this, it's learning a filter here that's going to extract from the image distinct attributes. In the same, similar to the filters that we've run in the computer vision class last week, that we manipulated the image to look in, and then the image became different in different ways just by applying simple mathematical techniques. Now, what this convolution filter is doing, in very general terms, is doing the same thing, but it's doing it automatically. Now, and then it's generating distinct types of images that we call feature maps. Each one of these images are going to be representing one particular feature of the original image, right? And then because this is quite complex, then there is a process of subsampling where we just reduce the size of these feature maps, and we can apply convolution again and find more precise filters until this becomes input to a fully connected neural network that's going to operate the classification. Now, this is what happens. So this, if we input this image here, a 6, this will be the first feature maps found by convolution. Then the pool maps, we're going to reduce the size just to reduce the complexity of the input. And then there is a new set of feature maps that's obtained by convolution again. So you can see here, we can see the sort of pattern that this kind of found the negative of the number 6 of the input, and this one found the inside of the input, and this kind of found a blurred image of the input, and so on and so forth. So we can sort of recognize what pattern these first convolutional layers found. But now, once we go to a second level, this is actually finding more complex patterns in the image. And in the end, what we have is a classification of an input of a number, and then the neural network will just recognize, oh, you just wrote a number 6. We can play with this. We can play with this. Again, let me open, oops. Let me open this website, which is here, right? So this is the example. Let me draw a, whoops, that's not drawing the wrong place. Drawing a number 1. So this is the input image. These are the features that was obtained by this process of convolution. Similar to what I presented in that slide, right? This is the first pooling layer. That's just a less complex image than this. It's just a smaller image than that. And this is the other convolution filter, and you can see that the system found as first guess the number 1, and you can see this lighting up in this neuron, output neuron related to the number 1, right? So let's draw something else. Let's draw number 3. Again, we found as the First guess number 3, second guess number 1. Now let's torture this a bit. Let's do something like this. So first guess is still 3, second guess now is 0. What if I do something like that? Oh, second guess is 8. So now it's looking like an 8, right? And the first guess is still, now it found that the first guess is 8 and the second guess is 3. All by finding these little patterns and then operating that this perceptron-like computation with this kind of in this neural network to be able to classify this number as 8. So you can see that the other values, there were other values that were lighted up. So 3 was also a possibility. I think was a second guess. Then 9, then 7. So you see, if you write like this, it could be anything, right? It could be anything. Right, okay. So I'm going to skip that and show. So that's all what I had to talk about neural networks. Maybe I will spend 5 minutes talking about my work in AI. So my work is basically applying all of these ideas in a sort of a humanoid robot setting, or it could be any sort of robot setting. Maybe I'll show you. This video is more interesting, where we have a robot soccer domain with this let me get. So we have these 4 robots. One robot red, one blue, and one purple. These are observer robots. In this work, this particular piece of work, the idea was to use the observations from these 3 robots to guide one of these robots. So this robot has what we call sensory deprived robot. It has no sensor at all. So you can see that it's kind of blindfolded. So a blindfold of the robot just to represent it as being sensory deprived. So, and then we use all of these ideas of recognition, perception, and also translating into natural language processing. So this robot is being guided by, in terms of natural language, to the goal. The goal is the ball. And we also use probabilistic algorithms because the position of the robots and the position of this robot is unknown, as well as the position of every other robot. So they had to be inferred by the observations, and the inference is given by the sensor data, and sensor data is noisy. So we have to apply a number of we have to apply probabilistic inference. So let me run this quickly. Okay, here is the blindfolded robot. These are the robots observing, trying to find the target. The target is both trying to find where the ball is and where this robot is. Once they found it, now they create a number of particles which are possible locations for this robot. And now they are telling this robot, the blindfolded robot, where it should move to in order to reach the goal. And at every step, there's a number of another particle distribution. Each particle is a probability distribution of the possible location of this robot, and not only location, but also the pose of the robot, the direction where the robot is going. And again, it's going to be redistributed. And in the end, the robot reaches the ball. And yeah, that's the end of this experiment. If you want to read more, these are the papers where I present. This is the paper where I present these results. It was published in the Spatial Cognition and Computational Journal. There's quite a few other papers that you could read if you are interested. Now, I know it was pretty dense and pretty rushed up, but I think as a brief introduction to AI, in 30 minutes, that's the best that anyone can do, really. But now it's up to you to follow the links and learn more about AI. I'll upload a few links on Flow as well next to these when I upload these slides shortly. Now, Industry 4.0, I promised to give you an introduction to Industry 4.0. I say that it's just the normal evolution of industry using the technology that's available, that's currently available to increase production capabilities, just like the other industrial revolutions before. Whereas if you get the Industry 1.0, was the first industrial revolution in the 17th century, where we had the use of water and steam powered machines in the production. We had production capabilities increased. It was the beginning of the division of labor, and business grew from individual cottage owners to very complex organizations. And we see this. This is a picture of a 17th century factory where we can see clearly the steam engines and the division of labors. And yeah, so this was the beginning of industrialization. And with all the impacts that it had on both on increase of production, development of products, reduction of prices, and also impact on the labor quality and also the beginning of the labor unions. You all know more about this than I do. Now, Industry 2.0 is defined as the beginning at the beginning of 20th century. Instead of steam engines like in Industry 1.0, it was the use of electricity as power sources. Machines became more portable. There was a mass production of goods using assembly lines, and the beginning of study of production optimization. That's basically the beginning of scientific management. We all love this film, right? We all love this film. This is a great representation of Industry 2.0. All right, once again, just keep chopping, getting into the machine. That's beautiful. Yeah. So this is an amazing film, and it really represents what Industry 2.0 was about. Industry 3.0 is the final decades of the 20th century. This is the typical robotization and automation, heavily automated industry. We use as transistors and integrated circuits, fully automated individual machines to supplement and replace operators, development of software systems, fast communication, use of fast communication, global market, pressure to reduce costs causing exodus of production to low-cost countries, formalization of supply chain, and so on. And finally, Industry 4.0 has most of the things that we've seen in this course. For instance, advanced robotics with the use of collaborative robotics. I think you've seen 3D printing in another class. Artificial intelligence and computer vision. Big data is a part of artificial intelligence, but just with the use of great quantities of data. Intelligent and flexible and distributed production, flexible use of collaborative robotics. We didn't see IoT, Internet of Things. Unfortunately, this is more related to networking. It's the network of machines, and with machines with some artificial intelligence, machines are capable to interpret its sensors and make inferences. And it's well known as the Industrial Revolution based on cyber physical systems. What are cyber physical systems? The definition, this is a great definition that I found on this blog. A cyber physical system is a system of collaborating computational elements controlling physical entities. Cyber physical systems are physical and engineered systems whose operations are monitored, coordinated, controlled, and integrated by a computing and communication core. They allow us to add capabilities to physical systems by merging computing and communication with physical process. That's your Zumo for you. That's the cobots for you. and with the use of artificial intelligence, and this just enhances it. This is a kind of a nice depiction of the evolution. So Industry 1.0, mechanic action in steam powered weaving room. Industry 2.0, mass production assembly line, electrical engineering, energy. Industry 3.0, automation, computers and electronics. Industry 4.0, cyber physical systems, Internet of Things, and networks. That's where we are at today. And I ask you, what about the robot apocalypse? Where are we at our project of destroying the world with robots and artificial intelligence? Let's see a state-of-the-art robot, what it's capable of. Whoops. Thank you, and yeah, I hope you enjoyed that, and I'll see you in the workshop. Bye.